So today we're going to be talking about section 8.4, which is on graphing rational functions. Now, what is a rational function? A rational function is an equation that's in this form right here. So f of x is equal to a of x over b of x. So you can see both of them, top and bottom, are going to be some sort of a polynomial, meaning, has x's in it, right? But obviously you know that this b of x, the bottom, cannot equal 0, right? And so we're going to have lots of different things we can have, okay? Lots of different graphs we're going to have. So here we go, okay? So a of x and b of x are polynomial functions with no common factors. So we would have had to divide out all of our factors as possible, right? And the bottom obviously can't be 0. All right, f of x has a vertical asymptote whenever b of x equals 0. So whenever the bottom is equal to 0, right, that's our vertical asymptote, so the up and down one, right? So that would be this one right here, okay? That would be when b of x equals 0, right? The horizontal asymptote, this way, right? Or I guess I should make it a dotted line. The horizontal asymptote, that's when, okay, it says, okay, here's a couple things, right? The first one, it says if the degree of a of x is greater than the degree of b of x, there is no horizontal asymptote. Okay, so for example, if we have like an x squared on top and an x on the bottom, there's going to be no horizontal asymptote. If the degree of a of x is less than the degree, it's going to be at 0. And if the degree of a of x equals it, what we do is we take the leading coefficients and divide them, and that'll be some number, some fraction, some number, something, and that'll be where it is, okay? All right, so here are a couple examples that they have in here. The first one is no horizontal asymptote, so you'll know that that's x squared over x plus 1. And you'll notice that this one, the degree is bigger, right? And so there's no horizontal asymptote. In this one, 3 over x squared minus 1, or no, excuse me, x to the third minus 1, you'll notice that the bottom will equal 0, so x to the third minus 1 equals 0 when x equals negative 1 and x equals positive 1, right? So we have two vertical asymptotes, right? We have one here at negative 1 and one here at positive 1. And then finally, here's our example. We have 2x plus 1 over x minus 3. And so you'll notice that my vertical asymptote is at 3 because the bottom, b of x equals 0 when x equals 3. So we have our vertical asymptote right here at 3. And then you notice that this is power 1 and this is power 1. So if there's a little ghosty 1 there, you just take this, 2 divided by 1. And so our horizontal asymptote is at 2. Okay? Now, let's look at an example. Okay, it says graph with no horizontal asymptote. All right, so we notice that we have x to the third over x minus 1. So first thing we're going to find is we are going to find our vertical asymptote. Okay, and that is going to be when x minus 1 equals 0. So then that's going to be when x equals 1, obviously because 1 minus 1 is 0. Okay, so if I was going to graph this, right, and you can use Desmos whenever you want, that's totally fine. I know on the quiz you got to use Desmos, basically graphing too, and that's totally good. All right, so we're going to have a vertical asymptote at x equals 1, right? Now the next one, we notice that the power right here is 3, and the power here is 1. And since 3 is greater than 1, there's no horizontal asymptote. Okay, so you're probably wondering what this is going to look like. Okay, so what we can do to make sure we look at it is we're just going to go to Desmos, right? And okay, we go to Desmos, graphing, and ours was x. Let's see. See, x to the third. Okay. To the third divided by, and then it was x minus 1. Okay. And so you'll notice, what does my graph look like? Okay, so it's kind of interesting, but it kind of does this curly thing as it goes down. So it starts up here and comes down towards that 1, obviously, and then it comes down and then back up. Okay, so if we want to go back here, it's going to be, I'll do it in red. So it kind of came down here, down like that, and then it went back and up. And this is just a free draw. I mean, it's not perfect, and that's okay. No big deal, right? Okay, so that's what we look like. All right, so here's a couple examples, a couple functions that you can graph as well. Okay, example 2. Example 2 says a boat traveling upstream at r1 miles per hour during the return trip to its original starting point, and a boat traveling r2 miles per hour. The average speed for the entire trip r is given by this formula, 2 times r1 r2 divided by r1 plus r2. Let r be independent variables and let the big R be a dependent variable. Draw and graph if R2 equals 10 miles per hour. So really what they're saying is, what is this graph, big R, going to be if R2 is 10? So we would say 2 times R1 times 10 all over R1 plus 10, right? And so we could make this a little easier. It's 20R over R plus 10. Okay, so if we wanted to look to see what our graph would be, right? Again, I can do this on Desmos. And remember, I have to use x's and not r's. So it's going to be 20x divided by x plus 10. Okay, so here's our graph right here. Right, there it is right there. I can make it a little bigger, but it looks something kind of like that, right? And so if you wanted to free draw that, I'll just do that over here on the side. Okay, you'll notice it kind of goes like that, right? And it says, what is the r-intercept of the graph? Okay, so basically it's saying if the up and down, where does it cross the y-axis, but it's saying r. And so we look right there, it crosses at 0, right? Okay, so crosses when r equals 0. And so we're going to say that. So that's at 0. What domain and range values are meaningful in the context of this problem? So if I go back, you'll notice obviously you can't have negative speeds, right? So you can't go this way. So really it stops here and it stops here, okay? So when it says what domain and range values are meaningful, you would want x to be greater than or equal to 0, or I guess we're not going to use x's, we'll use r1s. So it's going to say r1 has to be greater than or equal to 0, and big R has to be greater than or equal to 0 as well, right? And so if you graph it right here, okay, you'll see that it starts at 0, 0, and it has to go up from here. So that's our domain and range. Okay, here's a similar looking problem that you can try too. Now, the next thing we're going to talk about is called an oblique asymptote. Now, what is an oblique asymptote? Okay, well, what an oblique asymptote is it says when we have f of x, okay? F of x being ax over bx, and a and b are polynomial functions with no common factors except for 1, and b of x is not equal to 0, then f of x is an oblique asymptote if the degree of ax minus the degree of bx equals 1. Okay, so what does that mean? If you look right here, we have an example where it's x to the fourth plus 3x squared to the third over x to the third minus 1. And so you'll notice that x to the 4 minus 3, 4 from the top, 3 from the bottom, equals x to the 1. And so now we get what's called an oblique asymptote. And what that means is it means our asymptote is actually going to be the function x plus 3. Okay? Right? It's x plus 3. Now, how do you get x plus 3? Well, we're going to look at an example right now. Okay, now this function's written really small, but this is what it says. X squared plus 4x plus 4 all over 2x minus 1. Okay, so first off, we're still going to find our vertical asymptote. Okay, and that's when the bottom's equal to 0. So we'd say 2x minus 1 equals 0. Okay, so add 1, and then you get 2x equals 1, and so then x equals 1/2, right? So our this is going to be our vertical asymptote. Now you'll notice that the power of this is 2 and the power of this is 1. And so what ends up happening is we actually are going to, well, you know what? I'll tell you what. Why don't we graph this and then we can look at it, okay? So keep this in mind. What does this look like? Okay, what did the example before look like? Okay, so I am going to clear all my writing here. All right, but let's graph this. Okay, so it says it was x squared plus 4x plus 4, and all of that divided by 2x plus 1. Okay, so you'll notice again that, oh, maybe I did that wrong. No, I didn't. Okay, my vertical asymptote, it appears to be at negative 1/2, but I'm not quite sure why. So you added 1 and divided by 2. Maybe did I type it in? Oh, I did. I typed it in wrong. Okay, there we go. It's that positive 1, which we knew that. Now, you'll notice that it's following along this line right here, okay? Here's our oblique asymptote. It's a diagonal, right? And we have the number 3, 5, and we also have the number -2, 0. Now, how can we figure out a line that contains both of those, or at least goes through or is really close to both of those? Well, what we can do is we can say, let's do a little bit of investigation. Okay, so if we have the point 3, 5, and we had the point -2, 0. Okay, so if I was going to find the slope, remember that's change in y over change in x, right? So that would be 5 minus 0 over 3 minus -2, which would be 5 over 5, which is equal to 1, okay? So that's our equation would be, or our slope would be 1, so it'd be y equals 1x. And then what would I add if I multiply this by 1 is -2? What would I add to this number right here to make it equal to 0? Or the same for 3. 1 times 3 is 3 plus what equals 5? Well, that would be 2. So what exactly is how we find our oblique asymptote? Well, what we're going to do is we're going to take 2 points and find the slope in between them. So this right here, our asymptote, is going to be this line right here, x plus 2. That's interesting. So if we were going to graph it ourselves, or we can just look at Desmos, this is what it ends up looking like, okay? All right, so here's a couple others that we can try. You know what? Let's try 3a together as well. Okay, so first off, we know our vertical asymptote, right, is going to be x minus 2 equals 0, right, when the bottom is equal to 0. So when x equals 2, so we'd have a straight up and down line through 2, right? Okay, right there. And we notice that x to the second and x to the first, okay, subtract is 1 oblique asymptote, right? And so we have to figure out what that x is going to be. Okay, well, let's figure this out. Let's try another example and see if we can see a pattern or something that we notice. So it's going to be x squared divided by x minus 2. Okay, so we have the point 0, 0, and 4, 8. What do we do? What's it going to be? Well, okay, let's think about it. It would be 0, 0, and 4, 8. Okay, so if we found the slope in between them, y2 minus y1 over x2 minus x1, right? I would get, let's see, 8 minus 0 over 4 minus 0 would equal 2. And then you'd say, okay, well, 2 times 0 is 0, so add nothing to it, or 2 times 4 is 8, so add nothing to it. So my equation is going to be y equals 2x. I wonder how we get 2. Well, we can keep trying a bunch of different ways, okay? But that's going to be our oblique asymptote. All right, the last thing we talk about is something called point discontinuity. And what that is back in example 8.1, we looked at a bunch of examples where you could get rid of something from the top and bottom, but you still had to say the bottom couldn't be that. Okay, so for example, if we have x plus 3 and x minus 1 all over x minus 1, we still said we wouldn't want x to equal 1, because if we did in the original problem, even when they canceled out, you would get a 0 on the bottom. And so that had a special name called point discontinuity. And so that's what we're looking at. So even when you can take a factor out, the bottom still cannot be 0, right? And so what ends up happening is in our graph, there ends up being a hole right there. So even though the graph is continuous, it goes on forever, there's still a little hole missing in it. And on Desmos, it's a little bit harder to find, so you have to really be looking for it. Okay, so here we go. It says, all right, graph with point discontinuity. All right, so if I'm going to factor the top and bottom, and this is a difference of squares problem, so it's going to be x plus 4 and x minus 4, right? And on the bottom, I also have x minus 4. So when I cancel out the x minus 4s right there and there, I end up with just the function x plus 4. So my graph is going to look something like x plus 4, okay? The only difference is I'm going to say x cannot equal 4, okay? So if I'm graphing this, okay, and you know how to graph this function right here, x plus 4, and I'll do that in purple. Okay, it starts at 4 on the y-axis, and the slope is 1, so you go up 1 over 1, up 1 over 1, up 1 over 1. Now I've got to 4, and I have to make an open circle, up 1. Or I could go down 1, back 1, down 1, back 1, down 1, back 1. And so my graph looks just like this, but there's a little missing hole when x equals 4, because in the original function f of x, that value would be 0 on the bottom, which is undefined. So let's look at it on Desmos and see, and I can show you what I mean by it's a little hard to find. So it's x squared minus 16, and that whole thing divided by x minus 4. And so you'll see it looks like a nice straight line, but as I get close to 4 and as I'm approaching 4, you'll notice that on my graph it says 4 is undefined. So they don't do a very good job of drawing it, but essentially at 4, right there, is an open circle, right? So that is called point discontinuity. Point discontinuity. And we'll talk about continuity in later math classes, specifically calculus and pre-calculus, okay? And there's a couple problems that you can try as well. Obviously, they're going to have point discontinuity, and you'll have to figure out what those values are, okay? Good luck, and hopefully you don't have too many issues with this next section.